Hello everybody, welcome to the fourth episode of me learning Rust. Today we'll continue with chapter 3 and talk about functions as you see before you. For that, let's create a new project called episode 4. I know I'm not very consistent with my naming of projects, but bear with me. Let's go to episode 4 and go into Visual Studio. So let's start. So functions are prevalent in Rust code. You've already seen one of the most important functions in the language, the main function, which is the entry point of many programs. You've also seen the fn keyword, which allows you to declare new functions. Rust code uses snake case as a conventional style for functions and variables names in which all the letters are lowercase and underscore separate words. Here's a program that contains an example function definition. So Rust likes to declare functions the same way as variables. Great, so let's look at this. Okay, we have the function main that prints hello world, which is default, and then I have another function which is not declared, and I'm declaring, oh, that's interesting, I'm declaring the function after I'm using it. So let's declare another function and print here another function. Okay, let's cargo run this. See that it works. Great. So I'm printing hello world and then another function. This is great that I can declare a function after I use it, that the order of the declaration of functions is not important, because otherwise I'd have to think all the time when I'm defining some sort of part of the architecture of my program. Where should I define this? It's like the include hell that you get in C. So this is good. So let's read on. We've defined a function in Rust by entering fn followed by a function name and a set of parentheses. The curly brackets tell the compiler where the function body begins and ends. We can call any function we've defined by entering its name followed by a set of parentheses. Because another function is defined in the program, it can be called from inside the main function, not that we defined another function after the main function. In the source code, we could have defined it before as well. Rust doesn't care where you define your function, only that they're defined somewhere in a scope that can be seen by the caller. Okay, that's interesting. The wording here suggests that I can also do something like this, and it should work. It doesn't produce an error? Yeah. So that means that the functions are an object for the compiler that can be defined. They're not some special case for the language. And probably I think that maybe scope rules also apply. Let's try something like this. If I do this, would this produce an error? Yeah. So here I've defined this function in a subscope of the main function, and that means that I cannot call this function from here. That's important for clean code. Sorry, I'm using one hand because of my mic. For clean code, it allows you to define functions that you can use only internally, like private functions. I don't know how objects and classes work in Rust. We'll see it in the future. I'm not even sure that Rust is object-oriented, but I think it is, if I remember correctly. Okay, so let's continue. Let's revert back to the function as it was. It runs, everything is good. Let's continue reading. Let's start a new binary project, name functions. Started one. Place another function example in the main RS and run it. We did it. We got this result exactly like this. The lines execute in the order in which they appear in the main function. First hello world message prints, and then another function is called and its message is printed. Very straightforward, nothing new except the scoping thing. Parameters. We can define functions to have parameters, which are special variables that are part of a function's signature. Where a function has parameters, you can provide it with concrete values for those parameters. Technically, the concrete values are called arguments, but in a casual conversation, people tend to use the words parameter and argument interchangeably, for either the variables in a function's definition or the concrete values passed in when you call a function. Okay, this is for new programmers. In this version of another function, we add a parameter. Let's see, we're adding a parameter x, which is I32, and we're printing the value of x is. So the value of x is, and then we print the x, and here I'm calling the function with 5, remove the hello world. Looks okay, let's run it. Compile and run, yeah, and it prints everything as it's supposed to be. Yeah. The declaration of another function has one parameter named x. The type of x is specified as I32. When we pass 5 into another function, the print line macro puts 5 where the pair of curly brackets containing x was in the format string. I see no ID hint here about the type of the function. What if I do something like this? Will it like it? It doesn't like it. So, okay, that's interesting. There's no like auto casting of numbers here. Although the compiler is fully capable of doing this without me intervening, it doesn't like me putting a different type here. This is good to know. I think it's part of the safety that Rust's supposed to provide to the programmer. So if I put a different type, even if the type is convertible to I32, in this case, it will still throw an error just so I can fix it. And of course, if I'm doing this, if I'm doing this, this should work. Great. Okay. In function signatures, you must declare the type of each parameter. Yeah, makes sense. This is a deliberate decision in Rust design. Requiring type annotation in function definitions means the compiler almost never needs you to use them elsewhere in the code to figure out what type you mean. The compiler is also able to give more helpful error messages if it is known what types the function expects. Yeah, that makes sense. That means I don't have to put this. I just put 5, and if somehow the compiler can't make 5 and I32, it will throw an error. Let's just try something like this. This will not work, but if I'm doing this, will this work? This will also not work because it says it can convert U8 into I32. This is good. That means I can't do some C magic where I put characters and treat them as bytes to do some arithmetic. I think here I have to be more explicit about these kinds of conversions, and I think it's good. It removes some of the obfuscation that you can get with C. Let's go back to 5. Okay. So, when defining multiple parameters, separate the parameters declaration with commas like this. Yeah, makes sense. Let's put an H here, and we need a character here. And we print the character here. So let's run this, and I already see that the IDE helps me and tells me which parameter name it is. Still without type, but we'll see. Maybe like with, wait, if I hover, there was something when I hovered. No, nothing. Okay, here I can see the types if I hover over the function. Okay, great. This example creates a function named, I didn't rename my function. The first parameter name value is an I32. The second is char. Sorry for naming my variables like this. When I'm doing actual programs, I tend to use better names for my functions. This is just for testing, just to see that the language makes sense to me. We run the code and we get this. If I do this without the space, I will also get, yeah, great. Because we call the function with the 5 as the value and h is the value for value and h is the value for unit label, the program outputs containing those values. Okay. Statements and expressions. Function bodies are made up of series of statements optionally ending in an expression. So far, the functions we've colored haven't included an ending expression, but you have seen an expression as part of the statement, because Rust is an expression-based language. This is an important distinction to understand. Other languages don't have the same distinction. Let's look at what statements and expressions are and how their differences affect the body's function. Okay, this is something new. Statements are instructions that perform some action and do not return a value, and expressions evaluate to a resultant value. Let's look at some examples. We've actually already used statements and expressions, creating a variable and assigning a value to it with the let keyword in the statement. Okay. So we have a main function. Let's delete this. And we do let y equals 6. It's an I32. Yeah. So function definitions are also statements. The entire preceding example is a statement in itself. Statements do not return values, therefore they can't assign a let statement to another variable, as the following code tries to do. Okay. So let's make sure. I'm not expecting this to work, but let's say let z equals 6. This is probably have an error. Bind the value to a variable. Okay, that is just an error saying I can't do this. Okay. When you run this program, the error you'll get look like this. It was, yeah, this was the error. Plenty of errors. The let y equals 6 statement does not return, in our case it was z, does not return a value, so there isn't anything for x to bind to. This is different from what happens in other languages such as C and Ruby. Yeah, in C I can chain definitions and values. Where the assignment returns the value of the assignment. Okay, weird wording. In those languages, you can write x equals y equals 6. Yeah, this is C. And have both x and y have the value 6. This is not the case in Rust. Okay, I think I've never used this type of notation because it's just confusing. It's better to define everything separately for readability and for better debugging. Expression evaluate to a value and make up most of the rest of the code that you'll write in Rust. Consider a math operation such as 5 plus 6, which is an expression that evaluates to a value 11. Expressions can be part of statements in listing 3.1. The 6 in the statement let y equals 6 is an expression that evaluates to the value 6. Calling a function is an expression. Calling a macro is an expression. A new scope block created with the curly brackets is an expression. For example, okay, this is new for me. I'm doing let y equals, and I'm opening a scope, and let x equals 3, and I guess this gives the value without semicolon. This gives the value, and y will get. Let's just print. Let's print y is, let's run this, and we get 4. Okay, so the scopes are basically expressions, and if I'm not doing this, will this compile? No, because this one is an empty tuple. Yeah, so okay, so yeah, we read in the previous episode that this is an empty tuple. It used something like void, which is a value I guess you cannot assign. It's like an empty expression result. I still don't know what the rules in Rust about using this and how I can use it. I hope somewhere down the documentation we'll see examples for it. For now, let's return to this version of the code. So the expression in this scope is a block that in this case evaluates to 4. This value gets bound to y as a part of the let statement. Note that x+1 line doesn't have a semicolon at the end, which is unlike most of the lines you've seen so far. Expressions do not include ending semicolons. If you add a semicolon to the end of an expression, you turn it into a statement, and it will then not return a value. Keep this in mind as you explore functions, return values, and expression next. Let's make sure. Yeah, that's also evaluates to an empty tuple. And now to an I32. This is, I'm not sure if it's good or not, but if this is the only way to return a value, then there's no other way to use it. Let's see if there is a return keyword. No. Okay, there's exclamation mark. So no. So this looks like the only way to return values from a function or from a scope, which is sometimes useful, sometimes just confusing. I like to be explicit about what gets returned from a function. This is a little less obvious. But we'll see. Maybe this is just something you get used to and you don't worry about. Okay. Functions with return values. Okay. Functions can return values to the code that calls them. We don't name return values, but we must declare their type after an arrow. In Rust, the return value of the function is synonymous with the value of the final expression in the block of the body of a function. You can return early from a function by using the return keyword. Okay, so you can't return from a block, but you can return from a function. Okay. But most of the functions return the last expression implicitly. Here's an example of a function that returns a value. Let's declare this and play around with it. We have function 5, which returns an I32, and the scope is 5 without a semicolon. So if I'm doing this, let's just remove this. And I run this here, then this should work. I am going to try to do it inside the curly brackets, but I suspect it will not work. Yeah, I think only like variables work inside here. So this works. Let's see if I'm not declaring a return value. Is this an error? Yeah, it's an error. So we must declare return value, and let's try to return 6 here. And what's the warning? Warning, it's unreachable. This is okay, but let's see that it prints 6. Yeah, it prints 6 and warns me that this code is unreachable. I think when we will do flow control, then this will work. Like if I do some if statement or something that returns based on some arguments. Okay, let's continue. There are no function calls, macros, or even let statements in the 5 function, just the number 5 by itself. That's a perfectly valid function in Rust, though not very optimal. Note that this function's return time is specified too as an I32. Try running this code. The output should look like this. Yeah, we had a similar result. The 5 in 5 is the function's return value, which is why the return type is I32. Let's examine this in more details. There are two important bits. First, the line let x equals 5 shows that we're using the return value of a function to initialize the variable. Because the function 5 returns 5, that line is the same as the following. Second, the 5 function has no parameters and defines the type of the return value, but the body of the function is a lonely 5 with no semicolon because it's an expression whose value we want to return. Let's look at another example. So we're getting 1 plus 1 plus 1, which gets an x, which is an I32, returns an I32, and is equals to x plus 1. Sorry, x plus 1. So now we have to call 5 with 5, and this will, not 5, plus 1, and I'm expecting to have, again, 6 printed here. Yeah. Running this code will print the value of this is 6, but if we place a semicolon at the end of the line containing 1 plus x, changing it from expression to a statement, we'll get an error, yeah, as we saw before. Okay, the main error message, mismatched types, reveals the core issue with this code. The definition of the function plus 1 says that it will return an I32, but the statement does not evaluate to a value, which is expressed by the unit type. Okay, it's called the unit type. Therefore, nothing is returned, which contradicts the function definition and results in an error. In this output, Rust provides a message to possibly help rectify this issue. It suggests removing the semicolon, which would fit the error. Let's see. Let's see where it suggests to remove the semicolon. Yeah. Help remove this semicolon. Great. So this was functions. Let's continue to comments. Okay, I think this is a very short paragraph. Comments, just like C comments. Hello. Multi-line comments looks like this. We can do comments after the line. And within functions. Okay, this is the only way. How about like this type of comments? Does it work? Multi-line comments, sorry. Yeah, look, let's compile this. Yeah, so it doesn't say that you have this type of comments here, but looks like they're supported. Let's go to next part, control flow. Okay, now we're getting into some advanced programming. Okay, great. Let's delete this. Okay, so we have control flow. The ability to run some code depending on whenever a condition is true, and to run some code repeatedly while a condition is true, are basic building blocks in most programming languages. The most common constructs that let you control the flow of an execution in Rust codes are if expression and loops. If expressions. An if expression allows you to branch your code depending on conditions. You provide a condition and then a state. If this condition is met, run this block of code. If the condition is not met, do not run this block of code. Create a new project. Okay, we'll not create a new project, but we'll copy this. So now we have let number equals 3. It's an I32 by default. If number is less than 5, print true, and else print false with just one exclamation point. Okay, let's run this. Let's get our true. Yeah. So basically the difference I see here that you don't have this kind of syntax here, or maybe it works. It works, but it says it's unnecessary. Okay, so parentheses are not mandatory with if statements. Yeah, I think if you really want to have the parentheses, you could just turn off this specific warning. Yeah, we'll see. Maybe I like having no parentheses. I've never used, I think, a programming language. Oh no, there is Python. But yeah, we'll see. We'll see if I choose to use this or just remove the warnings and use parentheses. All if expressions start with the keyword if, followed by a condition. In this case, the condition checks whether or not the variable number has a value less than 5. We place the block of code to execute if the condition is true immediately after the condition inside curly brackets. Block of code associated with the condition in if expression are sometimes called arms, just like the arms in a match expression we discussed in chapter 2. Optionally, we can also include an else expression, which we choose to do here, to give the program an alternative block of code to execute should the condition evaluate to false. If you don't provide an else expression and the condition is false, the program will just skip the if block and move to the next bit of code. Yeah, that makes sense. Let's try changing the value number to a value that makes the condition false. Let's do this. Run and get the false. Yeah. It's also worth noting that the condition in this code must be a bool. If the condition isn't a bool, we'll get an error. For example, try running the following code. Okay, this is interesting. So unlike C, where numbers by default are true if they're non-zero and false if they're 0, here I really have to give it a Boolean type. Okay. If the condition evaluates to value of 3, this time Rust will throw an error. The error indicates that Rust expected a bool but got an integer. Unlike languages such as Ruby and JavaScript, Rust will not automatically try to convert non-Boolean types to Boolean. You must be explicit and always provide if with a Boolean as its condition. If we want the if code block to run only when a number is not equal to 0, for example, we can change the if expression to the following. Okay, let's do this and then we'll try something else from C that looks like it works. If I do this, will this work? No. So this is not something I can do here. There is not a not operator, but if I'm doing this, maybe the not operator exists. Yeah. So the not operator must be applied to a Boolean type. Yeah. Great. Oh. Okay, handling multiple if conditions with else if. You can use multiple conditions by combining if and else in an else if expression. For example, this. So I'm not going to write this, but I can see that there is no special keyword for else if. You just have to use else if, because there is just a cascade of arms until you reach the last else statement. The program has 4 possible paths it can take. After running it, you should see the following output. Okay, the only thing I want to test here... No, actually no, because this is a different scope. So I don't see anything important I want to try here. Yeah, and because I cannot declare new variables inside an if, then putting let inside here will result in an error either way. So let's just continue. When this program executes, it checks if expression is in turn and executes the first body for which the condition evaluates to true. Note that even though 6 is divisible by 2, we don't see the output number is divisible by 2, nor do we see the number is not divisible by 4, 3, or 2. Yeah, because it exits. If I put 6 here, this should be printed, and then it just continues to the end of this scope and not checking the other if or going here to this else. Yeah. Using too many else-if expressions can clutter your code, so if you have more than one, you might want to refactor your code. Chapter 6 describes a powerful Rust branching construct called match for these cases. Yeah, we saw match. I think it like prettifies all the options, but I haven't seen the complete power that match have. We only saw that enums can have values in them, and they can use this inside a match statement. So in chapter 6, we'll learn about it. Using if in a let statement. Okay, that's good thing I didn't put let inside. I really wanted to try, but apparently there is a solution for doing this. So because if is an expression, we can use it on the right side of a let statement if assigning the outcome of variable as listed here. Okay, yeah, that's cool. So let's test this. I have a condition. Let's do it from the top. I have a condition. Let condition equals true. And then let number equals, number equals if condition, typos, if condition, then 5 and else is 6 and semicolon, and then I print line, of course. Number is number. Let's run this and get 5. I put a false here, then I will get a 6. Yeah, makes sense. Very nice. Let's see if multi-line works. Something like this. Try to format maybe like this. Yeah. What happens if I format? Okay. We'll see how the formatting goes when I go over the 80 character line or something. Okay. So remember that blocks of code evaluate to the last expression in them, and numbers by themselves are also expressions. In this case, the value of the whole if expression depends on which block of code executes. This means that the value that have the potential to be results from each arm of the if must be in the same type. The listing 3.2, the result of both the if arm and the else arm, were i32 integers. If the types are mismatched, as the following example, we'll get an error. What's the error? If and else have incompatible types. Okay. And the fact that it says incompatible, let's try this. Okay. And what if I use this? Okay, so there is no implicit conversion even here. Okay. What if I do this? Okay, it's already, wait. Yeah. No implicit conversion. Great. Then I'll get this error. The expression in the if block evaluates to an integer, and the expression in the else block evaluates to a string. This won't work because variables must have single types. And Rust needs to know at compile time what type the number variable is definitively. Knowing the type of number lets the compiler verify that the type is valid everywhere we use number. Rust won't be able to do that if the type of number was only determined at runtime. The compiler would be more complex and would make fewer guarantees, just like JavaScript, about the code, and Python actually. If it had to keep track of multiple hypothetical types for any variable. Loops. Repetition with loops. It's often useful to execute a block of code more than once. For this task, Rust provides several loops, which will run through the code inside the loop body to the end and then start immediately back at the beginning. To experiment with loops, let's make a new project called loops Rust has 3 kinds of loops: loop, while, and for. Let's try each one. The loop keyword tells Rust to execute a block of code over and over again, forever, until you explicitly tell it to stop. Yeah, I'm not going to run this, but just maybe there's some kind of warning here, or let's see. Okay, no warning, but this will run forever until I Control C out of it. Okay. Okay, the symbol C represents that you press the Control C. You may or may not see the word again. Yeah, it depends, I think, on the buffers. Okay. Fortunately, Rust also provides a way to break out of a loop using code. You can place a break keyword and it will break out. Similar to C, don't need to put semicolon. I don't have to. What? Let's run this. Just want to see that it print high once. And let's see if it returns a value or some sort of type. No. So it doesn't matter. I don't have to put a semicolon at the end, but if I put a semicolon, it doesn't mind. Not even a warning. Okay. At the time, break. Keyword within the loop to tell the program when to stop executing the loop. Recall that we did this in the guessing game in chapter 2 to exit the program when the user won the game by guessing the correct number. We also used continue in the guessing game, which in the loop tells the program to skip over any remaining code in this iteration of the loop and go to the next iteration. Yes, that's C-style loops. So except the loop keyword. Returning values from loops. Ooh, that's interesting. One of the uses of a loop is to retry an operation you know might fail, such as checking whenever thread has completed its job. You might also need to pass the results of that operation out of the loop to the rest of your code. To do this, you can add the value you want return after the break expression. You used stop the loop. That value will be returned out of the loop, so you can use it as shown here. That's interesting. Let's see. I have the counter, mutable counter equals 0. Of course, it's i32, and let result equals loop where counter plus equals 1. I wonder if there are plus plus and minus minus shortcuts here. Let's just check. No. What it says? Use plus instead. Okay. So if counter equals 10, so after 10 iterations, break and return counter multiplied by 2. So I'm expecting to get a 20 return here, and it's of type i32. This is of type i32. Everything makes sense. I think I need a semicolon here, right? And then I can print the result and it should print 20. Let's run this. Yeah, makes sense. Let's read this. Before the loop, we declared a variable named counter and initialized it to 0. Then we declare a variable named result to hold the value returned from the loop. On every iteration the loop, we add 1 to the counter variable and then check whenever the counter is equal to 10. When it is, we use the break keyword with the value counter multiplied by 2. After the loop, we use a semicolon to end the statement that assigned the value to result. Finally, we print the value in result, which is in this case 20. Yeah, makes sense. Really cool thing about the language, I can assign out of the loop I think makes it more compact, more understandable. Overall, I don't have to assign to a variable inside the loop and then go find it. I can see that the loop returns an I32 here. Yeah, it's good. Loop labels to disambiguate between multiple loops. Ooh, that is missing from so many languages. If you have loops within loops, break and continue apply to the innermost loop at that point, like in most languages. You can optionally specify a loop label on a loop that you can then use with break or continue to specify that those keywords apply to the labeled loop instead of the innermost loop. Loop labels must begin with a single quote. Here's an example with the two nested loops. Okay, this is a new syntax. Let's write this. So we have let mutable count equals 0 as before, and then I'm starting a labeled loop like counting up colon loop. So this is a loop labeled counting out. I print count equals count, and then I declare another mutable variable remaining that is 10, and then I loop again. This time it's not labeled. I print remaining equals remaining, and then if remaining is a 9, oops, sorry, used to it. If remaining is 9, then I just break, and if count is 2, then I break counting up. And here remaining minus equals 1, and here count plus equals 1, and I print and count equals count. So let's try to figure out what we'll print, and then we'll see if we're right. So count starts at 0, so the first print will be count equals 0. Then we have the remaining. Then this loop starts. We print remaining, so we have count 0, remaining 10. This will not go here. This will not go here. Then remaining will be one smaller. We loop again. We print remaining equals 9, and then we break out of here. And then we continue to count plus 1. So we have count 0, remaining 10, remaining 9, and then we'll have count 1. After we have count 1, we go here, we have remaining 10 again. And then this is not true. And then we have remaining minus 1. So I'm expecting to have count equals 0, remaining 10, remaining 9, count equals 1, remaining 10, remaining 9, and then count equals 2, and remaining equals 10, and then it should break here. And at the end, the count will be 2. So let's run this. Oh, the print will not run. Let's see. So 0, 10, 9, 1, 10, 9, 2, 10, and then the end count 2. Okay. This is as expected. Everything makes sense. And this breaks out of here. I wonder if I can return a value. Let x, and then here I'll do this. Sorry, and I return count. Count plus remaining. Yeah, it works. And I have to put a semicolon here, and I can also print the x here. And it's supposed to be 12, I think. Yeah, great. So this also works. I can break to a label with a value. Excellent. The outer loop has the label counting up, and it will count up from 0 to 2. The inner loop without a label counts down from 10 to 9. The first break that doesn't specify a label will exit in the inner loop. Only the break counting up statement will exit the outer loop. This code prints, this, conditional loops and while. Okay, let's delete this and move on. A program will often need to evaluate a condition within a loop while the condition is true. The loop runs. When the condition ceases to be true, the program calls break, stopping the loop. It's possible to implement behavior like this using a combination of loop, if, and else, and break. You could try that now in a program if you like. However, this pattern is so common that Rust has a built-in language construct for it called a while loop, and probably like while in C. In listing 3.3, we see while loop to loop the program 3 times, counting down each time, and then after the loop, print message to exit. Let's do it quickly. Ut num equals 3, and then while, again without brackets, num this, print line num, and then num, increase the value of num by 1, and in the end print done. Okay, this should print, -1. Almost had an infinite loop. It should print 3, 2, 1. Yeah. Great. The construct eliminates a lot of nesting that will be necessary if you use loop, if, else, and break, and it's clear. While a condition evaluates to true, the code runs. Otherwise, it exits the loop, looping through a collection with 4. You can choose to use the while construct to loop over the elements of a collection, such as an array. For example, the loop in listing 3.4 prints each element in an array A. So let's define an array. A equals 10, 20, 30, 40, 50. And let mutable index equals 0. And while index is less than 5, print I'll just print the value itself. It's A. Yeah, I have to use this. A index. Yeah, so it's a prelude to 4 function, to 4. I need to increase index. This is why I use 4 functions, because then it makes you increment the value. Okay, so now it prints the array. Very well. Here the code counts up through the elements in an array. It starts at index 0 and then loops until it reaches the final index in this array. That is, when index is less than 5 is no longer true. Running the code will provide this. All 5 arrays values appear in the terminal as expected, even though index will reach a value of 5 at some point. The loop stops executing before trying to fetch a 6th value from the array. However, this approach is error prone, as you've seen. We could cause the program to panic if the index value or test condition is incorrect. For example, if you change the definition of a array to have 4 elements but forgot to update the condition to while index less than 4, the code would panic. It's also slow because the compiler adds runtime code to perform the conditional check of whatever the index is within the bounds of the array, or every iteration through the loop. This is what I talked about in a previous episode that I want to check if this is actually an overhead and what is the overhead and what are the suggested ways to loop over arrays. Okay, so this is a more concise alternative. You can use a for loop and execute some code over each item in a collection. A for loop look like the code in listing 3.5. So let's do a for loop. Let's just do it like this. For E in A. I don't need to increment anything, and I can just print the E inside here. Less code. There's a warning. Yeah, I don't need this index anymore. Less code works the same, and also if I add another value here, this will still run without me changing anything about the loop. Okay, let's continue. When we run this code, we'll see the same output as listing 3.4. More importantly, we've now increased the safety of the code and eliminated the chance of bugs that might result from going beyond the end of the array or not going far enough and missing some items. Using the for loop, you wouldn't need to remember to change any other code if you change the number of values in the array, as you would with the method used in listing 3.4. Okay, that's what I said before. The safety and conciseness of for loops makes them the most commonly used loop construct in Rust, even in situations in which you want to run some code a certain number of times, as in the countdown example that we used a while loop in listing 3.3. Most Rustaceans would use a for loop. The way to do that would be to use a range provided by the standard library, which generates all numbers in a sequence starting from one number and ending before the other number. Here's what the countdown would look like by using a for loop and another method you've not yet talked about, rev, to reverse the range. Okay, let's copy this code because I want to try some stuff, and I think where the video is a little long, let's just run this. We get 3, 2, 1 liftoff, but as I remember, if I do this, I'm going to have 4, 3, 2, 1 liftoff. Wow, this is a long compile time, but yeah, as I expected. And the code is a bit nicer. Yeah. Okay, summary. You made it. This was a sizable chapter. You learned about variables, scalar, and compound data in a previous episode, types, function, comments, if expression, and loops. To practice with this concept discussed in the chapter, try building a program to do the following. Convert temperatures between Fahrenheit and Celsius, generate the nth Fibonacci number, print the lyrics to the Christmas carol, The 12 Days of Christmas, taking advantage of the repetition of the song. When you're ready to move on, we'll talk about a concept in Rust that doesn't commonly exist in other languages, the ownership. So let's do, I don't know, everything looks pretty simple. So we'll leave it for the next episode. We'll start with doing just one of these, and then we'll continue to the next chapter, which talks about ownership. Thank you and goodbye.